Welcome back to electrical circuits videos. This is the second video regarding on electrical circuits. And here we want to discuss two topics, which is critical. One is ideal circuit model. First, the reason we do ideal circuit model or circuit models is that because if you drawing and putting physical shapes together really doesn't help in understanding how they behave and coming up with a relationship that helps us design future product. By modeling things and then drawing it in a more simplified logical form, allow us to take advantage of the relationships such as Ohm's law to analyze the circuit and understand it. What do I mean by that? So if you look at, for example, if you look at a resistor, a typical resistor will come in different shapes, and they have color bands on them that describes what values they have. But we don't really want to be sitting there and drawing colorful devices in various shape and forms if you want a resistor. So basically the decision is that we will, anytime we want a resistor, we just draw it with a couple of up and down arrows, and then we will put the designator, like if it's an R1, R2, and then we will put the value on it. If it's like 100 ohm, we put 100 here. If we want a 1K, we would put a 1 kilo ohms, or whatever the value is, we do that. So the resistors are represented this way. And anytime, so here, for example, in this particular, let me make this a little bit smaller. So for example, in this particular picture, I have a resistor that is 100 ohm, and I'm calling it R4, and I have another resistor which is 250, and I have another resistor that's 40, another resistor that is 500, and it shows me how they are connected to each other. This one is connected in one end, this is connected in the other end, and all of that. Okay, so that our resistors are one thing that we use. The other component we use in the ideal circuit, we're talking about our ideal circuit model here. The other two items that we gonna use in this, there are more components, but for this course and for this video and what we're gonna do here, we're gonna focus on a resistor and collectively power sources. So power sources, we can have two kinds. We can have a current source as it's showing here. And what is a current source? A current source basically guarantees you an amount of current regardless of what voltage you need for that current to stay there. Okay, and I'll get back, and we're going to do another diagram to describe what that means. But a current source is basically an arrow showing the direction of the current, and we'll have a designator or something like I1 or something like I2, I3 if they are more than one. And then it will tell you how many milliamps is it guaranteed to give you at any given point of time. For example, this particular current source will give you 200 milliamp regardless of what else is happening in your circuit. You can count on it to give you 200 milliamp every time you use it, because these are ideal circuits. And then this the other component. So the third component we use is this one, and this over here is called the voltage source. And a voltage source is basically guarantees a voltage from this point to this point for you. In this case, it says it's 5 volts, which means the voltage from here to here is going to be 5 volt, plus sign on the top, minus sign on the bottom. Okay. So these are the components we use in an ideal circuit. Now, ideal circuit has some specific characteristics. There are three characteristics for ideal circuit that you need to be aware of. One, so let me shrink this out so I can kind of write it here so we remember. Actually, let me do this. I'm going to go ahead and copy it from someplace else I have that information. All right. So an ideal circuit. So an ideal circuit will have all of these three characteristics. So what does it mean that electricity moves instantly through the wire? What that means is that when you make a change in one part of your circuit, the rest of your circuit instantly see the effect. So you don't have to wait for the effect to get from here to here. That happens instantly. So from point 1 to point 2, it's going to be there's zero time elapsed for whatever you did to point 1 to see the effects on point 2. It's going to go everywhere. Okay, so that's this one. So there is no delay in an ideal circuit model. So what the ideal circuit does for us is basically these are the assumptions for an ideal circuit, which allows us to do a bunch of things without having to worry about the complexity that comes from these various things. The second assumption that it does, it says that current through all part of a branch or a wire is the same. So what does that mean? That basically means that if this is a branch, let me make this a little bit smaller. Let me go to green, and let's make it a little bit smaller. So this wire here, and here is called a branch. Since this is all connected and is going through one device, this is called a branch or a wire connecting all of this. So what the second ideal circuit assumption is telling us is that when if the current here is a certain amount, the current here would be the same, the current here would be the same, the current here would be same. Since, for example, when we look at this circuit, we know that this current is 200 milliamp through this device, which means then the current here is 200 milliamp. The current here is 200 milliamp, and the current here is 200 milliamps, and the current here is 200 milliamps. So everywhere is the same. Okay. So that was the second one. The third one is pretty important as well. The second one basically says, if I take all the power in a system and add them together, that would be equal to 0. So basically, if you take all the components' power and you add them all together, you'll end up equaling 0. Okay, if it's a valid circuit, for a valid circuit. Okay, so it's interesting because that basically means that part of the circuit is generating electricity, part of the circuit is consuming the electricity, and all of it's staying in the circuit. If the wire is not connected, no electricity comes to the circuit, no electricity leaves the system. Okay, so that's great. This is kind of good. So now we know what a ideal circuit model is. Got three components, got a power supply, can be a voltage source, can be a current source, and it's got a resistor. And there are three assumptions that go with it. Electricity moves instantly through the wire, no delays. It's everywhere in the circuit, all at once. Number two is current through all part of a single wire or branch is the same. So it doesn't matter whether you measure it here, 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 or here. All of that current will be the same. The third assumption is that the sum of powers in the circuit is equal to 0. This we need to do a little bit more discussion, and we need to be talking about what is this passive convention business. So let's go ahead and move to that and start a little bit of a conversation about what is a passive convention, what does that mean, and things of that nature. Okay, let's go ahead and start by introducing what a power is, what are the equations for power, and then we come back and talk about what passive convention says. Let's get the new page. Let's move our page a little bit so we get a clean page to work with. Okay, so that's good. So passive convention the power is defined as voltage times current. So we have three types of devices. We have resistors, we have power source. It really doesn't matter what you have. If you kind of generalize it, generalize whatever is in the box, it could be a power source or it could be a resistor in the box. And if you come in and this is plus, this is minus, and the current comes in here and the voltage is here, if the current is coming in to the positive terminal of a voltage, then you can use this equation to do that. This is referred to as a passive convention. The reason they call it a passive convention, if you do it this way, then if the power is larger than 0, if the power is positive, then that indicates that you have a passive device, meaning what is a passive device? Passive device basically says you are consuming energy. So for example, a resistor would be a passive device. Okay. So because the current goes in, voltage gets generated in the same direction as the current. And so the power for this would be P equals to V times I. And don't get surprised, they could apply the Ohm's law to this thing. And basically, if you apply the Ohm's law, you could go two ways. You can say, okay, I'm going to replace the V as I times R. And if I do that, then P becomes I squared R. Or you can use the other Ohm's law, form of Ohm's law, and say I is equal to V over R. And if you do that, then power becomes equal to V squared over R. Okay. And as you can see, I is always squared, V is always squared, which is positive, R is positive. So the resistors always for resistor power is positive because they're always consuming power. They take electricity and generate heat. That's their job. Their job is to consume the power and generate heat. So for example, if you have a baseboard heater at your home, that's a big giant resistor. If you got a cook electric stove, that is basically a giant resistor. That is taking electricity, generating heat. Now, how about, so for example, if you have, on the other hand, these relationships here, of course, only work if the device is a resistor, but this equation works everywhere. Now, if you were to do this and you find that the power is less than 0, then you have an active device. So if your power is negative, you have an active device. And this is only true under passive convention. And passive convention is the way we analyze circuit. That's universal in the electrical engineering. So passive convention is what is used. And these are the rules. If the power is larger than 0, is passive. And when there's less than 0, is active. Now remember, you can only apply this relationship P equal to VI if the current is flowing into the positive side of this. So let's do some examples of where that is not the case. Then you say, okay, what can I do? Start. So let's go down here and do an example of another device. So let's say someone gives you a power source, a voltage source, and say this is plus, this is minus. And they say the current is going this way, and I is, let's say, 10 amps, and this is 8 volts. So you say, wait a minute, if it's a passive convention, if I want to find the power for this, then P is equal to V times I, but in order for me to use that, I have to make this device such that if this is plus, this is minus 8 volts, I want the current to come this way. But when I look up there, the current is going the other way. So you can flip the current as long as you add a minus to it, okay? And if you add a minus to it, then you're okay, which means what happens when I do the power, which is V times I, it's going to be 8 volt times minus 10, and that will be minus 80, which tells me it's less than 0, which this is a generating power. Okay. So this now see what interesting thing happened. Remember on the on one of the assumptions on ideal circuit was total power consumed by a circuit is equal to 0. Now let's see if we can kind of work on this and figure that out for a very, very simple circuit. So let's say we have a simple circuit, and our circuit is something like this. We've got a source. We use a voltage source, it's 10 volts, and we just have a resistor across it, and the resistor is let's say 5 ohms, something simple, 5 ohms. Okay, and they're asking us, is this a valid circuit? We say, if you want to know if it's a valid circuit, then some of the power has to be 0. If true, is valid, right? That was kind of the definition, one of the third assumption on the model. So now we say, okay, how do I do the power? Well, we know that the voltage from here to here is going to be the same as 10 volt. Okay. So I could since this is and I know that the current comes out of the positive side of a source that way. So what would be the current? So we know the currents are going to be same everywhere. So 10. So I use the Ohm law, I equal to V over R, and therefore 10 over 5, and it's 2 amps, and we're good to go. So 2 amps there. So now I see that the current is flowing through the positive side of this. So power for the resistor is going to be equal to IV times I, which is going to be 10 volt multiplied by 2 amp, and it's 20 watts. Now, when I go over here and try to find the power for the source, I say, okay, what is the power for the source? And I look at this thing and I know the current, unfortunately, the current is going away from that, and it's equal to 2 amp because the current's first, or the second assumption, the ideal circuit was that in a given branch or a given wire, doesn't matter where you measure the current, it will be exactly the same. So if its current is 2 amp here, then the current here will be 2 amp. The only thing is I want the current. If I'm going to use P equal to V times I have to have my current coming in to this. So if that is it, the way we draw this is when you opposite arrow, you have to make sure you make it a minus, so you can still keep the actual current still going the other way. This is mathematically showing it going in, but the -2 says it's really not going in, it's going the other way. So V times I would be 10 times -2, which says power is -20. Oh, okay. So, and so if we know that this therefore is less than 0, so this is actually generating power, it's an active device, and we know that this one is positive, therefore is consuming power. Okay, so what is the sum of power? Sum of power would be -20 for the power source plus 20 for that. So yes, indeed is equal to 0, therefore it's a valid circuit. So that's kind of the definition, if you will, of passive devices versus or passive convention. How do you do power calculation in passive devices and things of that nature? Okay. There are a number of examples in the section 3.4 and 3.3 of the textbook. 4.3 and 4.4, chapter 4 of the textbook, and you're welcome to go take a look at that and try to try to kind of apply it yourself and see how that works out for you. Okay. Let's see. So at this point, we've learned enough that we can actually start modeling things ourselves if you wanted to. For example, a flashlight. If you think about a flashlight, you got a battery in there. So let's say we have a flashlight with a couple of AA batteries in it. So if I have a couple of AA batteries in it, then each AA battery is 1.5 volts, and typically they have one connected to the other. If these are AA batteries, they are kind of connected like this. This would be 1.5 volts, 1.5 volts. So this is about 3 volts, let's say. Okay. And then the wires have some loss, usually it's pretty small. You got a switch to turn it on and off. By opening it, you're breaking the light, so no electricity flows, no light. And then the light bulb, usually somewhere between 4 to 8 ohms, somewhere in that range. So when the electricity voltage goes through, as the current flows through the light shines. Okay. If it's an LED, it'll be the same similar concept. LEDs are a little bit different, but regular light bulb, the old-fashioned light bulbs, are just a resistor that heats up and close. The LEDs are a little more complex, and I'll leave that for a different time. So what I'm saying is that by just simple modeling stuff that we've done so far, we are getting to a point where we can actually make some models of things and think about it. The other one is like a human being. For a simple model of a human being, if you're trying to figure out what type of electricity does to humans, it would be something like this. Your typical, of course, every human is slightly different, but on the average, your arms look like a 400 ohm resistor. Your torso, the main body, look like 50 ohms. So the thicker the portion, the less resistor, more easier for electricity to go through it. The thinner it is, you can see the torso is the thickest, so it's got the lowest resistance. The legs are next bigger thing, and that's 200 ohms, and the arms are the smallest ones, so they are 400 ohms. So you literally can figure things out by modeling it like it was an electrical circuit. For example, if someone comes and let's do an example of this one. Let me zoom in so you can see the whole thing. And then there has been physiological studies done on humans. They know, for example, if you get electricity through your body, depending on how many milliamps go through your body, how does your muscle react? If it's 3 to 5 milliamp, you barely notice it. 35 to 50 milliamp, you get some pain. Extreme might be a strong word. 50 to 70, your muscles paralyzed. You might have heard people hold on to the electric wire, somehow accidentally touch the electric wire and they can't let it go. That's because their muscles have contracted and they have no control. Their brain cannot control it because the brain controls your muscles using microamps. So if you put milliamps, which is 1,000 times bigger, your brain signals don't get into your hand. You want to open your hand, but the electricity is forcing it to close. And if you happen to have 500 milliamp go through your heart muscles pretty much stops, which is not a good thing. You'll have a heart attack. So we are able to analyze this. For example, if somebody says, "Hey, what happens if I touch electricity that comes out of your typical home?" A typical home has 110 volt electricity on average coming. So what happens, let's say if I've got a bare hand and I touch those, okay? And then you say, oh, that's pretty easy. These guys are not connected. So I know that I've got 100 volts here. I've got 450 and 200 here, which means the total resistance, I sum all of these together, is 650 ohms. This one plus this one plus this one, because the electricity will flow where it can. The parts that are not connected to anything, electricity doesn't flow through it. So electricity flows this way. And so you want to know how you're going to feel. So you're going to have basically 110 volts divided by 650 ohm. So you should not be feeling it too much, but that there are exceptions to that rule. So I don't want you to walk away and touch the wall because of insulation and other things that happen before the circuit kicks in. The circuit breaker kicks in, you will get a really high voltage, much higher than 110 volts across your skin, and you can get a burn or other things. But you can use these concepts to do analysis of different voltages, different signals, and kind of see what happens as these things are happening. Well, let's do a calculation on this and see typically what happens. So if I take 110 volts and divided by 650, even not considering the special circumstances that happen, that tells me I've got 0.169 amp, or another way to put it, 169 milliamp. So if you look at it, and I go back to this table, I'm falling somewhere in the range above muscle paralysis and heart stopping, and of course not a good place to be. If you have a weak heart, you might have a heart attack. If you have a strong heart, you're just gonna really painful experience. So the moral of the story is don't stick your finger in the wall. Okay, and of course, your washer, dryers, and other things in the home is even have higher voltages, so it's even more dangerous than this. And there are other effects that happen because of the instant connection to the electricity, but we won't get into that. But just enough to know that you can use the simple Ohm's law and resistors and the power sources, voltage source, current source, to make a lot of determination about your environment and how you will interact, or how things work and how you interact with electricity. There are more examples for you to do. Let's do one more before we move forward. For example, they give us this circuit and say, hey, why don't you analyze this and tell me what the value of R should be. And they say it's a valid circuit. As soon as they say it's a valid ideal circuit, that means all the rules apply. One rule was that the current, right? The current through this circuit is going to be the same here as it's over here. One way would be to say, okay, I can add these two resistors together and kind of redraw my circuit. We are getting a little bit ahead of ourselves, but that's okay. So it's 10 volts, or I can do sum of powers. I think it's easier to do that. So we have two resistors, and I'm going to turn everything to ohms. So I'm going to say this is 5K is 5,000 ohms plus R, because they're kind of connected in one end. It's called series, and you can just simply add it. And the current through here is 1.9 milliamps, which another way of writing is 1.9 times 10 to the minus 3 amp. You notice I'm turning everything to amp, volt, and ohm. This way I don't have to worry about, funny things happening. Everything is going to be either amp, volt, or ohms. So if I do that, then I say, okay, that's great. So now what happens? Ohm's law tells me that the voltage, which is here and says this is 10 volt, this voltage is also 10 volts here. So all I'm going to do is says, okay, V is equal to I times R, that is the Ohm's law. So I say, okay, 10 volt is better be equal to 1.9 times 10 to the minus 3 times 5,000 plus R, right? So that's pretty cool. So I'm basically now I can find R because I can multiply these two together and move it to this side. If I do that, it's going to be 10 minus 1.9 times 5, because the 1,000 and 10 to the 3 cancel each other out, equals to 10 to the minus 3, so times 1.9 times R, right? I multiply them through. Okay, so if that is the case, then I can go back up here and continue if you don't mind. So my R will be equal to 10 minus 1.9 times 5 divided by 10 to to the minus 3 times 1.9. Yeah. So when I calculate this, I find my R is an answer to the question. So most of the examples in this section and the homework for this section pretty much wants you to remember what the assumptions are for ideal circuit. You need to remember Ohm's law. You need to remember the passive convention and P equal to V times I. If you remember those things, will be all you can take care of almost all the problems in here. Let's take a quick look at the problems in this section. See if I have them up or I gotta go find them. Oh no, I got it here. Okay. So some of the problems in this section you can work on is things like describe the 3 assumption of ideal circuit model. Yeah, I know that. Electricity moves instantly. The current is the same in all throughout the branch, and total power in a circuit has to equal to 0. What are the 3 different ways that Ohm's law can be shown? We've been through that. Calculate the power, as you know, as this is moving in this direction, and it's we always in a resistor, always in a resistor. When a current comes in, current always goes through the positive side and comes out the negative side. And since I have I can use P equal to V times I if I want, or I can use let's use this one. What is the V here? I have Ohm's law, which is I times R. So I can plug in I have I 5 milliamp. I have 6 kilo ohm as R, so I have the V. And the current is moving to the positive side, do that. Here, voltage and currents are given, but current is going to the minus side, so you gotta figure. So remember, that means the current is coming out of the positive side. You gotta flip it, which means you gotta use a minus sign to flip it. Okay. Let's see what else we got here. Some of the other problems, most of them are of that form. 6 basically says, gives you a relatively simple circuits, calculate the I. You say, oh, I know these guys are connected in this direction, so 10 plus 40 is 50. I can use Ohm's law to find the current. Powers, you can figure that out. And then sum the powers. If it's equal to 0, you've got a valid circuit. If not, not. So these are the problems you could potentially, not potentially, you can solve with things we talked about in this video. That brings us to the end of the video talking about, that was covering 2 things. The ideal, let me go back to our scribbles, to ideal circuit model and the 3 assumptions that go with it. And then passive convention, which basically says, if you want to use P equal to V times I, you have to make sure that the I is flowing into the positive side. If it's not, you flip it, add a minus sign to the value, and you're good to go. By the way, just to make sure that it's clear to folks, if you have a circuit and the current I is going here, our assumption says that the same I comes out the other end. If I want to draw the I going this way, then I have to say minus I, okay? Now, on the other hand, if there is a voltage here, V, but I want to write it the opposite, I can do the same thing, but I have to add a minus sign to it, okay? That's all the differences. So let's say I here was 1 amp. This I then would be minus 1 if I'm going to draw the arrow going the opposite direction. If this was 5 volts, but I want to flip the polarity, then I have to write minus 5 on this side, okay? Instead of plus 5. That brings us to the end of this video. Thanks for watching.